Welcome, everyone. We'll be starting this session on emissions from mobile sources, commercial transportation, and inland ports. I'm Randall Martin, a HAQAST member.
Hi, everyone. My name is Dan Goldberg. I'm from George Washington University. I'm going to be showing a presentation evaluating the trends and spatial patterns of NOx emissions in urban areas using TROPOMI. Here we have a nice spatial image of what TROPOMI looks like here in Utah. This is taken from my paper a few years ago. You can see obviously the location here in Salt Lake City. We can see a lot of different NO2 sources here in the region, and you can very clearly differentiate that from the background. So I'll show a lot of pretty pictures like this throughout my talk. Okay. So before going any further, I really want to thank a lot of the collaborators on all this work, including those that were participating on the Tiger team that ended about 6 months ago now. This is the first time I'm giving a talk since the Tiger team concluded. So thank you to all the team members. I'll have their individual pictures on slides where they contributed. But I also want to thank the stakeholders as well. We've had a lot of stakeholders. I really, really value their feedback and their input to all the work that we've done on this project. So really couldn't have done this without them. All right, so we're going to start this presentation off with a question. Where do you think the worst NO2 pollution is in the world? And the caveat is 2022, as seen by satellite, and average to a 10-kilometer grid. Where do you think that is? China, India? It's not the US. I can show you that. It's actually not China. It's not India. It's not probably where else you're going to guess. Not Mexico City. Okay, I'll give you the answer. I even stumped Randall Martin this morning. It's actually Tehran, Iran. And that is, we Gage did a little deep dive here. That's because of some of the UN sanctions. They don't have any international automakers coming into their city anymore. They're just using older cars, and they're using technology that is internal domestic, and so their pollution is actually quite bad, and quite bad compared to every other city in the world. So exciting what we can use satellite data to investigate here. But this is a column content, but it's, I think, pretty likely they have, if not the worst, very, very close to the worst air pollution, NO2 pollution in the world. But we've also seen some changes over time. A lot of papers recently have looked at trends between, say, the beginning of the OMI record, which is 2005, and 2019, or sometimes 2020. But here I'm now comparing 2019 to 2022 as annual averages globally. We've seen some reductions in China. We've seen some smaller reductions in Europe. We've seen some increases in tropical areas. There's been some papers on this. And then we've seen mixed, but mostly down the US. And I'll talk about this in the next few slides. So different trends for different regions. I just want to put a plug real quickly for TROPOMI NO2.us. That's a website I continue to maintain. Here's just a daily snapshot. I'm not going to talk about now. Go check out the website, and I have yesterday's image there for you to peruse. But what I do want to show here is the recent NO2 trends. I'm going to show 2018 to 2023, but here's 2023 as at the outset here. We have the spatial image of this past summer and comparing this to the trends, the difference between the 2018/2019 baseline period that I'm using in 2023. We see reductions here in the Eastern United States. We see, which are probably driven mostly by the transition from coal to natural gas. So we are seeing some improvements in air quality because of that transition. We are seeing large reductions in California as well, and some in urban areas, not quite as dramatic in other urban areas outside California, and we have some small increases in the central US. I'm open to discussion about what's causing that. There's no clear answer, in my opinion, as to why that's occurring. But let's take a closer look at some of the individual cities. Here's Salt Lake City, where we are right now, New York City, Los Angeles, and Chicago. We see the trends over time. We're seeing some slight decreases over time in all of these cities, with the largest decrease in the Los Angeles area. I don't know if you can see these all the way in the back, but in Los Angeles area, we see about a 20% reduction between 2018 and 2023. Chicago, New York City, and LA are less than that. In New York City, it's actually most evident, where we saw the decline during 2020, the pandemic year, and then a recovery, but not a super recovery in most cities. So it's good that we're a little bit lower than we were before the pandemic. But what I like to put up here is that satellite data can provide these trends before an NEI is released. NEI comes out every 3 years. The 2023 NEI is not going to come out until March of 2026. So we can have an idea of what this year's trends of emissions are, in somewhat near real time. This is never going to replace the NEI, but it's something to get us an initial estimate of what NOx emissions look like this year before waiting 3 more years. This is for maybe some of the super users who've been using the offline data from the ESA website. They have been, they've released a new algorithm that's now version 2.4, but they've had version 1.2, version 1.3, and version 2.3. And each different year has a different algorithm. If you're just downloading the offline version, if you want to do long-term trends, you need to be looking at the reprocessed version, and you can see that the different colors are different values depending on which version you're using. Shouldn't be super surprising, but some years, such as the New York City in 2021, there's some big discrepancies on individual years and individual cities. So important to use a consistent algorithm throughout this entire time frame, and even note that 2.3 is not the same as 2.4. There can be some big differences, even if there's what appears to be a small change in the algorithm. All right, so now I'm going to talk about, that was all unpublished work, and I'm not sure if I'm going to publish that work, but now I'm going to transition to work that is going to be in the peer-reviewed literature. Some of the work that we've done as part of the Tiger team, which was looking at the intra-urban spatial variation of NO2. Now we can use TROPOMI data to possibly differentiate NOx emissions from highways, ports, airports, et cetera, within cities. And this has large applications for environmental justice issues and beyond within cities. So I want to thank Daniel Tong's team for providing the NEMO emissions inventory, which is shown in the far left-hand column there, and comparing that to the TROPOMI NO2 average. This is filtered further to look at days with stagnant wind conditions. So we're hopefully getting a close to an apples to apples comparison, because the NO2 is not traveling far from the emissions source on those days. And when we do a comparison, we see really excellent correlation when we divide these up into zip codes. So we just aggregate both the emissions inventory and the satellite data into zip codes. We do a correlation, and we get really strong correlation of about 0.8 in the 3 cities I'm showing here. I showed 10 cities in the paper, but there are some outliers, and that's what I'm going to talk about in a second. So want to reemphasize really good spatial correlation, but we're now looking at into the weeds here. What further can we do to improve the emissions inventory? And this has been driven a lot by Zach Adelman and G. Dickens at LAGCO, looking at some of the warehouse emissions and other on-road emissions within an individual area. And we can see that, just highlight here that some of the areas that are red, that the red areas are indicating a potential NOx inventory overestimate, and these are in wealthy neighborhoods. So wealthy neighborhoods are more likely to own EVs, more likely to own energy efficient appliances, et cetera. So maybe there's some reason to use some type of economic indicator in the emissions inventory. I don't believe that's currently available. If I'm wrong, let me know. And then also potentially there is a NOx emissions underestimate near rail yards, warehouses, and that is in the southwest location of Chicago. That's where there's a lot of these types, and we see somewhat could be an underestimate of NO2 and NOx in this region. I perhaps could have put this earlier, but there's a reason maybe I showed this. This is really using all the tools in our tool set to try and understand urban NO2. First thing is we want to understand the biases of TROPOMI in an urban area. Here we're comparing TROPOMI to the Pandora measurements in Houston area, and we're seeing really good correlation, at least in my opinion, of R squared of 0.62, but an important low bias of about 11%. This is even when we're reprocessing the air mass factor. It's a little technical, but some people will understand that. Then if we compare Pandora to GCAST, we see better correlation. So the thing GCAST is probably, it is picking up on the spatial heterogeneities of NO2 better in cities. I don't think that's a surprise to most people, but what was a surprise to me at least is that we see a very low normalized mean bias. So it's not only is the correlation great, but so is the actual, it's pretty close to the truth in the urban areas. And then we did a CMAQ simulation at 400-meter spatial resolution to try and match the spatial resolution of the very high GCAST measurements. And we see much lower correlation there and a lower bias, but a lot of the correlation is driven a little bit by some minor errors in wind direction. So I wouldn't read into the low correlation too much, but it does seem like this particular simulation had a low bias in NO2 that I'll talk about in this slide. So we have, we did a comparison between CMAQ and GCAST in the downtown area. The red is indicating that GCAST on the left panel is indicating that GCAST is larger than CMAQ, particularly in the downtown area. So what I really like about this is that you get different shades of red at different locations in the city. If you were using, say, OMI or even TROPOMI, you would get just a few of these red pixels, and it would be hard to really pinpoint exactly what's going on in the city. So I think this is some strong evidence for a NOx emissions underestimate near the downtown area, probably related to on-road emissions, which is what the right is showing, is that we are able to do a flux divergence emissions calculation on both CMAQ and the GCAST measurements. We found that the areas that were that had the biggest differences were near the roadways. So it does seem like we're able to highlight exactly that the roadways are likely a cause for the NOx emissions underestimate in the Houston metropolitan area. This is not the NEI. This is a TCAQ emissions inventory. So I wouldn't, and this is only for a single month. So it's hard to draw large conclusions about other areas, but I wanted to just show exactly how GCAST measurements can be used to get really high spatial resolution estimates within cities. So I'll just put these conclusions up. I'm probably out of time, but I'm happy to take questions. I think it's really exciting what we can do with TROPOMI, tempo going forward, and we really like to utilize the measurements from GCAST, which get us very high spatial resolution, can understand this intra urban heterogeneities of NO2.
Great. Well, thanks, Dan, for that interesting talk. And next we have Jen Kaiser from Georgia Tech.
Hello, everyone. I'm here on behalf of Ted Russell, who's one of the HAQAST members, and I'm a collaborator, a co-PI, I guess, on the HAQAST project. The work I'll be presenting is about how we've been blending CMAQ and TROPOMI to understand airports, seaports, and warehouses. The work I'll be presenting is not my own, it's of the people shown there. So former students Abby and Nash, now at the University of Connecticut as an assistant professor, and the EPA as a postdoc. And then Ariana Moore, now sitting in the 6th row of this room here. So Abby has been looking at airports, Nash at seaports, and Ariana at warehouses. So the thing that these have in common, in my opinion, is that they're all rapidly changing and important sources of pollution for urban air quality. Air travel across the US increases at a rate of 3% per year, and that's not slowing down anytime soon. So it's a growing source of emissions, whereas urban NO2 tends to decrease. That hot spot is getting brighter and brighter. Seaports have continual new regulations and rules. We'll give a case study for that out of the Port of LA. And then growing e-commerce is growing the importance or the relative importance of warehouses and where they're located, the emissions associated with your daily Amazon packages. This is a figure showing the number of new Amazon warehouses each year. That's the number of new warehouses, not total warehouses. So it's growing quickly so we can all get our next day shipments. So if we're trying to understand these things, these rapidly changing source sectors, we can look at TROPOMI NO2, which gives us rapid observations. I'm going to start with the airport. And this is the one I start thinking about immediately because Atlanta has the world's busiest airport. And it's located really close to downtown in the center, marked ATL in that purple box there. It's a brighter hotspot than the urban core. We also see hotspots located at the 2 power plants to the west and east of the city. On the left is TROPOMI, and in the center is CMAQ. And you'll see the typical pattern for when we compare satellite-based observations with CMAQ is that the CMAQ hotspots are brighter than the TROPOMI hotspots. So we see higher concentrations in the city and lower in the surrounding background. So what Abby did as a part of this work was she focused on just that one really bright hotspot located in the city and at Atlanta. She has other work, which I won't talk about the other sites as well. And the idea is, how can we make, what is the cause of TROPOMI and CMAQ looking so different? And why is that bright spot so bright in CMAQ? Well, one thing to note is that when you download, I guess, the basic CMAQ, the aviation-related emissions are allocated towards the surface at the airport. And we know planes don't just emit at the surface at the airport. They take off and they travel both vertically and horizontally. So this seems like a really easy first guess. What if we were to just reallocate the emissions according to common sense, put the NOx emissions where the planes fly? So that's what she did. And what I'm showing now is how that changes the agreement between TROPOMI and CMAQ. So on average, we have TROPOMI being higher than CMAQ across the city. That's just a normal bias we have, even when we correct for air mass factors. In gray are the original points, if we use the default point allocation of airports, and in black is if we make the emissions where the planes fly. So this tends to give a more uniform agreement of TROPOMI and CMAQ across the city. So this maybe gives us some confidence that this is a better representation of emissions in our model. And we know that this also changes the way that air quality is modeled for Atlanta. We see an increase in MDA8 ozone across the whole city, upwards of 4 parts per billion near the airport, which is not a negligible amount. So what I would say is that maybe what TROPOMI can do here is give us a check on our modeling of aviation-related emissions. But my personal take is that TROPOMI alone isn't enough. One of the maybe limitations here is how much we trust our satellite observations near an airport where you have emissions at various altitude. So I know that satellites are the darling of HAQAST and especially NO2, but I would say more observational constraints are needed, and NASA does suborbital work as well. So thinking about other data products that are available to us, Pandora's are very similar to satellite-based observations in that they can give you total columns of NO2. They can also give you vertical profiles. So ongoing work, we took measurements near the airport in 2020 and 2021. We're still processing that data. But ongoing work funded by HAQAST is in situ measurements of NO2 near the airport. It was also quite shocking to me that many of these urban sources of emissions don't actually have regulatory monitors near them. So that's something that these NASA sort of projects can help fund. We're also looking at how this sort of research grade or regulatory grade NO2 instrument can compare and supplement these low-cost sensors like QuantAQ. Moving from airports to seaports, this was a project by Nash looking at a rapid change in emissions again. This time, when we had that big logistics backup in 2021 that caused hundreds of ships to idle offshore. And we see here is a time series of, in black, the number of ships waiting to dock. There just was not enough space for them. So they were all just idling and emitting, and air toxics were building up. It was a big concern for the communities. There was then a rule put in place. You see that second line there where they said the boats need to wait about 40 kilometers offshore rather than right where the people live. So the boats waiting immediately near shore decreased. So this is a fun case study for TROPOMI. Can we detect the change in air quality related to when these boats were right by the shore and then when they moved further out? We can use TROPOMI to do that, but the key thing about NO2 columns is that they don't depend just on emissions. Changes in meteorology as well will change your NO2 vertical column density even under the same emission scenarios. What CMAQ allows us to do, or models, they allow us to ask what if scenarios. So what Nash did is he took the meteorological conditions during this period and modeled what the NO2 would have been under a normal emission scenario. So we have this correction for emissions. How much of the change in NO2 that we see during this time can be attributed to emissions alone? Once we have that part figured out, we can look at the emissions or the columns from this period to prior years and say the remainder part is from actually changes in emissions. And you can see that map shown here. And we have ground-based observations to support this overall change as well. So the good news is that this is now sort of a more permanent rule that the ships aren't going to idle right by the port anymore, and there's a air quality and safety region. All right, moving on to the last story of how we can combine TROPOMI and models. This is the ongoing project, which we've been working with many people as part of a Tiger team or rapid response project. And this is Ariana's work, looking at warehousing. And this is, again, a really difficult problem because it's a bump on top of the relatively large urban enhancement. It's not an isolated source we're going to see. So Ariana's been looking at this region in here in LA, where each point here is a warehouse. And we see that the hotspots in TROPOMI are correlated with warehouse, but also just general shipping and travel activity. An important thing that this project has shown us is that, when you download TROPOMI, baked into it is already some assumption about the vertical profile of NO2. If you replace that with a high resolution model, you'll get a different vertical distribution and a different overall magnitude. So what Ariana found is that you get an early 40% increase in TROPOMI NO2 when a high resolution profile is applied, which is an important thing to think about if you're trying to use these satellite products to understand urban air quality. What we see is that in general, TROPOMI is larger than CMAQ, except over LA, but we do see this large dependency on air mass factors as well. I'll encourage you to probe this topic more with Ariana at her award-winning poster. She won an award at CMAS just a couple of days ago. So you can stop by tomorrow morning to see that. So I'll leave you with 3 takeaways. And really, I know the title of this is mobile emissions, but within these 3 sort of sources of mobile emissions, I think there are 3 other points I wanted to make. Was that TROPOMI NO2 can be used as a check on emissions, but we're not done with ground-based observations. Models can help us separate the role of meteorology, and that while satellites are great, but not all emission sources are easily detected or separable at this city level, and how we think about our vertical distribution can make a large difference. All right, thank you for your attention.
Thanks so much, Jen. And our next speaker will be Zach Adelman from Lake Michigan Air Directors Consortium.
Thanks, Randall. Hello, friends. I'm going to talk a little bit about electrification of mobile sources and where I think we're in a current moment that we can all gather around and really make some progress towards. Start with a little introduction. What is LADCO? For those of you who don't know, we're one of 6 what's called multi-jurisdictional organizations, or MJOs, in the country. There's a map up there. We represent the 6 states in the Great Lakes region. We're federally funded by EPA. We've been around for, since the late 80s. And essentially what the MJOs do is we kind of sit in the space between state regulatory agencies and the federal EPA, bringing states together. Our board members are the air program directors, and we bring the states together to talk about regional air pollution issues. We do decision support as well. So LADCO, my staff, are modelers and data scientists and emissions experts, and we help states understand kind of what's driving air pollution. We typically work in the National Ambient Air Quality Standards, the NAQ space. We work on regional haze. So we do decision support. We also do, we're tables around which states can get together and talk about air pollution issues and try to come up with some common solutions. And one of the things that we're really looking at closely right now is, how do we leverage this mass capital that's coming down from the Fed through things like the Inflation Reduction Act to make progress? And we'll look at some charts here. These are emissions that we're looking at. And this is the Chicago non-attainment area. So all the counties that are in Chicago, we're looking at pie charts of NOx emissions and VOC emissions. And I've color coded all of the mobile source emissions, anything with an engine basically in blue. And so you can see that, 57% of the NOx in Chicago is associated with some sort of engine related source, on-road, off-road engines, rail or marine. VOC is a bit different. It's dominated by solvents. You've got biogenics, but mobile sources are in there as well, particularly on-road gasoline and non-road gasoline. And a lot of that is just coming from, gasoline use, fuel use. Looking at a different city, Cleveland, So we can parse the on-road diesel NOx here, and we'll look at this, the one biggest, contributor to NOx in Chicago, on-road diesel. And this is light, medium, and heavy duty. You parse that. And a nice thing about, looking at the NEI is the NEI provides a lot of granularity in the types of sources, the National Emissions Inventory. Long haul trucks. These are, according to the NEI, the biggest source of NOx emissions in that on-road diesel sector. But then you start looking at things like short haul passenger trucks. Transit buses are also a pretty good slice there as well. Long haul heavy duty diesel vehicles are about 56% of the NOx in Chicago from that diesel segment. Things look a bit different when you look at Cleveland. See, mobile sources are a much bigger slice of the pie for NOx, 72%. And if you look at that on-road diesel slice, it's even bigger. Parsing that, it's kind of a similar picture. Long haul is a big chunk. The buses, the smaller vehicles aren't as big a deal in Cleveland. It's long haul and short haul. Short haul trucks are things like box trucks, drayage trucks, things that are operating within the city. They're not driving across the country or driving long distances. It's important to look at this and parse this, because when we're thinking about controllable sources and controllable in the near term, like in the next few years, states don't have much regulatory jurisdiction over long haul trucks, right? These coast to coast vehicles, this is where they're having to look to EPA and federal agencies to deal with emissions from those sources. But there are some potential policy options for the trucks that are operating within the city boundaries, like short haul. Complicated map here on the right. Basically what this is showing is LADCO got a hold of some telemetry data from medium and heavy duty diesel vehicles in Chicago. And we were able to calculate each grid square in that right plot is a traffic analysis zone. It's about 1 square kilometer. And we could calculate the number of hours that the vehicles were spending within each of these traffic analysis zones. So you can see the kind of red colored, pink and red colored spots are like hot spots of where heavy and medium duty trucks are. So either there's a lot of trucks driving through those cells, or there's trucks sitting in the cells idling for a while. We superimpose that on a map of different land use categories, and we highlight land use categories like warehouses in blue. The green are intermodal facilities. So this is where you have freight going from train to truck, from ship to truck. Mostly in Chicago, it's from train to truck. And you can see that there's these hot spots of truck idling hours around the intermodal facilities. This makes sense. The trucks are driving in there to pick up and drop off freight. The map on the left is from a recent cumulative impact assessment that the city of Chicago did, showing where the environmental justice neighborhoods are and the kind of overburdened communities in Chicago. And, you see a coincidence between some of these idling hotspot areas and these environmental justice neighborhoods. So there's, these idling hotspots are also happening in these overburdened communities. We're having a moment. As you may all have noticed, there's a lot of money coming down from the federal government right now for environmental planning and environmental endpoints. And so mobile emissions are an area that, kind of impact this trifecta of targets for environmental improvement. If we can electrify vehicles, we're taking care of air pollution, we're taking care of climate, and with diesel vehicles, we're also taking care of some of the equity issues, addressing some of the equity issues with overburdened communities. The challenge that we're facing with all of this funding is timing and priorities. EPA is trying to get this money out the door very quickly. They're asking the states to come up with plans very quickly to prioritize the sources that they want to control. Here's tens of millions of dollars, state X. What are you going to do with it? What are you going to control? And so we in our membership, and I think this is happening elsewhere in the country, we're looking for like shovel-ready mobile source projects. Where do we help our states understand where to put this capital? Looking at a lot of different priorities, impacts, where are we going to have the most bang for the buck in terms of reducing emissions, health, equity, regulatory impacts as well. So can these sources be touched by regulation? Are they going to be creditable in a state implementation plan? What's practical? Again, I talked about the jurisdiction of short versus long haul trucks. What can states and locals actually control through their policy levers? Timing. We're not looking into the 2030s here. We're looking for things to happen within the next 2 to 3 years. The next ozone NAAQS attainment date is in 2027. And then we're trying to align all of this with IRA funding. So which sources can we touch and get to with some of the funding that's coming down from the Fed? So I have 3 points kind of to make here as takeaways, where NASA and you can help with this challenge. One is, I think, a synthesis and a meta-analysis of recent projects that have characterized the co-benefits, climate, air pollution, health of different emission sources would be really helpful right now. If this already exists and I'm not aware of it, please let me know. We can use that in our conversations with our states to help them start to understand, where are you going to get the most bang for your buck? Another thing that I've faced over the years at LADCO is the process, kind of the decision support and the planning process. The conventional process is we have a goal. We want to get to attainment of the ozone national ambient air quality standards, NAAQS. So we research solutions. We say, okay, what are the emissions reductions that we need to get? We do modeling, we do data analysis, we spend a year, we come back and we say, it's mobile sources, it's heavy duty diesel, it's the wildfires, it's the state next door. Policy assessment of our states kind of come back often and they say, well, we can't do anything about those sources. So then rulemaking, becomes difficult. We can shift that narrative, shift the process, and I think lead in some cases with what can you do? What is within your jurisdiction? What sources do you think you can control through your policy levers? Then use that to help drive research solutions, to help drive the research, right? So that at the point we get to rulemaking and the policy assessment that would come in on that kind of bottom line there, a policy assessment would happen again after the research solutions prior to rulemaking. There's more of a potential for the solution to actually be implemented. And we need to shorten the amount of time that process takes. And then the last point is, as we're seeing in this conference and elsewhere, the aggregation of data is happening. The collection of new data is happening and planned. We're seeing examples of where machine learning is being deployed to help us understand the information. But we really need to continue to push, and this is a call to you all in the research community, to really push the use of machine learnings to more rapidly assimilate all of the massive data catalogs and information that are coming into our space, into both research and decision making. I mean, if you look at the number of papers that are being published now in all of the journals, it's so hard to keep up with, right? So how do we aggregate this information and make it useful? The application and the policymaking timelines are a lot shorter, I think, than the research timelines, right? And we need to figure out how to use AI and machines to make that process more efficient. And I would, suggest that we start with this mobile source electrification optimization problem. The optimization question being, what sources do we go after for electrification? Is it the school buses? Is it the trash trucks? Is it the drayage trucks? Is it the off-road engines? It's going to be a different answer in different parts of the country, but I think using AI tools could help us figure that out. All right, thank you.
Thank you for that thoughtful presentation. Our last speaker for this session is Claudia Gillman-Acuña from the Chattanooga Hamilton County Air Pollution Control Board.
All right, isn't Chattanooga beautiful? All right, so I come to you as part of the stakeholders. So I have none of the expertise on any of the studies, but I would like to use the studies to help support what I see coming in the future, which is a little bit what you were talking about. So Chattanooga, has a population of about 375,000 people. So we're kind of like just there. We need to be within attainment, which we are. If the rules gets a little bit more stringent, we may not be. And I only have 3 monitoring stations. I have a PM 2.5 federal regulated, and I have 2 ozone sites. My PM 2.5 is set right downtown in the middle of it. And one of the major challenges I have right now, I'll go back to that one, is that we have a lot of traffic coming from Atlanta, lots of trucks. We're trying to bring in new businesses. And so we just recently got an Amazon warehouse, and we share a monitoring station with Georgia on Rossville. And somehow their concentration levels are a little bit higher than ours. And that is because they have a truck parking facility right next to their monitoring site. That's what I think so. We share all of our information with EPA, and so it's all available, raw data. And as you can see by the colors of my little table there, we mostly have lots of good green days or good air quality, except when we have exceptional events like the Canadian wildfires, and that sends us into the red. But those are stuff that we usually cannot control. In regards to mobile sources in airports and all of that, we are still under the standard, but it may not be so for too long. And so one of the challenges that we present as a small agency is there's a lack of interest from the public. They hardly go to our website. All they're interested is on allergy season, and that's all they know about. And so Chattanooga used to be one of the most polluted cities in the country, and now we're not. And so we lost a lot of boom and fantastic, PR and stuff like that. And somehow that is good because we're doing good. But I recently took on the responsibility for the air monitoring portion of it. And it's come to my attention that, we need to be a little bit more proactive. So I don't want to wait until things get worse to be able to do something about it. And so this lack of interest from people, the lack of studies, nobody's interested in doing some studies there. So that we are thinking maybe we can do some health related studies. And so we've been talking about it with the health department. lack of funding. I mean, we're a small agency and we depend solely on EPA grants and stuff like that. And the easy access to the information, like all in one place shop. Like I would love to go there and get everything that I need. And I think that was the motivation of me coming over here, was to kind of get informed and see where I can get the knowledge so I can help my community. And then the tools to engage the public and to create more awareness. Those are my challenges. And so with the lack of fun, I ended up deciding, well, let's go a little AI. And since the public is more interested in pollen season than they are interested in pollution, let's try to interest them into air pollution and health benefits and air quality by targeting and establishing pollen sensors. Until today, I have one guy that has been in the work in the same job for like 25 something years. And he's the one who goes out there every morning and he reads the pollen count for us. And everybody, I ended up figuring out after I took over that everybody counts on our agency providing the data to be able to make decisions about walking out in the park or staying indoors. And I ended up figuring out that nobody else was doing pollen. And so I said, well, how do I manage to get the two of them and get the community engaged? And so through some cooperation with a NGO, we decided to go from the reading everyday pollen to using AI to identify pollen, because these pollen sensors also have the capability of identifying PM 2.5. And so that way I can get some of the grant money to kind of get it in there and see if maybe I can help myself build a database and create a sense of community. And so we agree on the 10 of the municipalities we have on putting one pollen sensor and keeping one for investigation. So if there's a citizen complaint, then we can take that pollen sensor and mobilize it to the area. And at the same time, we're getting the PM 2.5 and PM 10 readings off of it. So this is my way of kind of getting around the system to try to get it funded, and at the same time try to get the community engaged. Now, does it have to do with air quality? Yes. Pollen necessarily has to do with respiratory issues, and a lot of people don't realize that, air pollution, it gets, the respiratory issues get exacerbated by air pollution and the seasonal allergies. And so we ended up thinking, well, we can do this, and maybe we can find some new solutions for the future. And so we are really, really tiny. And we are using, equipment to measure PM 2.5, the so-called T640, and then some 2025 eyes for filter-based PM 2.5, and then ozone analyzers as well. And so we're very tiny, but it doesn't mean that we're not trying to make a difference. And this is us. That's a small community, a small team of people. And so I hope that you guys can support us by providing us the information that we need. We want to make a change at local level as well. So that's it. Thank you.
Great. Well, thank you. And now I'd like to invite all our speakers to come up for a panel in the front. And we have time for questions from the audience. I see a question first from Michael here. I'll pass you my microphone.
Yeah, okay. Yeah. Just a quick question to Zach. I really liked your maps, your of the truck idling. How did you get the truck idling down to the zip code? That was amazing.
It actually is not at the zip code. It's a 1 kilometer by 1 kilometer traffic analysis zone. So it came from the Metropolitan Planning Organization, and they bought telemetry data. And then they aggregated the telemetry data into these traffic analysis zones that they use for their travel demand model, and then passed it along to us. They couldn't give us the raw data because of some proprietary issues, but it's access. Whenever we look at telemetry data, we find unbelievable insights, and we need to get more access to it. It's expensive, as you know, but I think as a community, we need to figure out how to get at it more regularly.
Great. And a question over here.
I have a quick follow-up question on that. The telemetry data, is it only when the truck is moving? Or I guess that it's like, do you know that it's actually idling and running? Or do you just know that's where it is? Because to me, knowing that it's in a spot doesn't mean that it's on.
Yeah, that's a great question. So there were some assumptions that we made about the amount of time that the truck was sitting in one location for a certain amount of time. And I don't remember what Mark Jansen is, our emissions guy at LADCO. I can get you some of those details, but basically after a certain amount of time, he just assumed that the truck was not running anymore. Heavy duty diesel trucks don't turn off that often, I'll tell you that.
Okay, other questions?
Thank you. Yeah, I wanted to talk about Atlanta and the CMAQ modeling there, and noted that, you know, there's a 20% low bias. I forget if it was NO2 or ozone, but probably both. I mean, I would imagine. So can we extrapolate that kind of result to other metropolitan areas? For example, Salt Lake City, can we assume that there might be like a lack of density, I guess, like in parts of the city?
Sure. So I would start by saying all data is local. So there are different reasons for differences between observations, whether they be satellite or ground-based, and models. And in Atlanta, there might be some problem with emissions, but in other places, I think meteorology could be a lot more complicated. So I would be wary of applying anything, just blanket saying, oh, it's low here. It would be low there as well.
Yeah, pretty much.
Brad Pierce, University of Wisconsin. This is to Jen as well. So my understanding of the airport emissions is there's kind of an assumption that a lot of it is ground, facilities. But there is, like within SEDS and various other, there are, three-dimensional aircraft emission inventories. Are you using those? And what's your thoughts about, how much of it is ground and how much of it is actual aircraft emission?
Great. So the question, how much is ground and how much is aloft, can be further separated into, I guess, the aircraft takeoff, landing, takeoff, and operation cycles versus cruising at altitude. And so the cruise at altitude is a separate, where they have where the location is. And so Abby's work first had to add that in, which wasn't involved at all in the original CMAQ modeling. And then on top of that, there was reallocating the landing takeoff LTO emissions horizontally and vertically. So two parts of that. And so the way that she decided how to allocate those was using the AEIC emissions inventory, which is what GeoSChem uses.
Right. First, I see Tracy.
Well, thank you all for your presentations. I think it was a really nice group of talks that ranged from policy applications where new data could be used to very advanced applications that pushed the data as far as they could go and maybe said it's not quite such a darling, although I think it is. But no. But I think the point is like, if you like, we could always do better. And with advanced models, you can push things much further. On the other hand, most resource constrained policy organizations don't have an in-house CMAQ modeler, don't have in-house, statistical optimization AI capabilities. So I guess I'd love to hear the perspectives across the range as to where you see and let's just take TROPOMI NO2 because it came up across these platforms. Like, where do you see speculatively satellite data being useful to a resource constrained non-research organization? Yeah, and maybe we could start with Jen, but I'd love to hear, but I know everybody up here can answer that question. I mean, and or like, what are the information needs around NO2 emissions where you'd like some information? Thank you.
I feel like I've been put on the spot, but I can start with my favorite use of TROPOMI and NO2, which is trends. I think if you want to know if something's increasing or decreasing, that's great. Also, if you want to know if this spot is more than this other spot, that's great. That's the thing I think that's a very low barrier for entry. Now, if you want to say, this is what TROPOMI sees, what is the emission from this car? I think that's where you need partners that have that sort of expertise.
Yeah, I can speak to what we've been doing at GW recently. For those not aware, Susan in the past has presented on our 13,000 cities studies, where we have estimates. We've done estimates of NO2, PM 2.5. I think we would do CO2 soon for 13,000 cities. So we're trying to do the work on our end to sort of operationalize images and trends and other things for 13,000 cities. Of course, many of them are in the US, but many of them are also internationally, and get them at least some basic information that could be really useful, such as, for example, we have Chattanooga NO2 trends for the last 15, 20 years on our website. So yeah, it's urban air quality.online, I think is still what it is. And that's using actually Randall Martin's product, but then also NO2 products that we have access to. So yeah, what we're trying to do is operationalize a lot of the stuff ourselves so that we just click a button and it does it automatically for 13,000 cities everywhere, and everybody can use it themselves. But to go to Jen's point, it's exactly correct. If you have specific problems in your city, it's going to be a little bit harder to do that. Just looking at long-term trends, if you want to regulate this particular power plant, this particular industry, you're going to have to hire somebody or come to us specifically.
I'm going to bob and weave and say it depends. It really depends on the application, right? Like, are you trying to look at a trends analysis to provide weight of evidence towards attainment for some national ambient air quality standard? Or are you trying to find locations where you need to be, for a monitoring plan? It really kind of depends on what the agency's goals are and what their resources are. I have this vision of fusing the satellite data, which is closer to the truth than inventories, but with the granularity, the source granularity that you have of inventories, to try to get a sense of what is emitting where. Because ultimately, if you have a non-attainment area or you're trying to reduce emissions, the question is well, what do I reduce and where?
All right, so like I was explaining, I just been in this position for about 5 months, and so when I came in, I was in the Jurassic period. Everything was on paper and nothing was digital, and so I don't have any of the digital data that was available to me. So I'm kind of like, I'm trying not to reinvent the wheel, but thank you for letting me know that you have the information. Because we are an attainment area, we no longer are measuring NO2, the VOCs. And so we only have PM 2.5 and ozone, but it doesn't mean that we may not necessarily need it in the future. And so I was thinking in the back of my head, maybe I should go back and look at those, paper numbers and see where was it, 10, 20 years ago, and kind of like go and make my own study. But this is just my wishful thinking, to see what we can do. So in the future, like I said, we can be a little bit more proactive. So since you have the data, which is the entire point of coming over here, I may go ahead and make use of it. But right now, one of my main interests is to find out around the highway portion of Chattanooga surrounding the downtown area. We don't have any sensors. There's some low cost sensors that are being provided by an NGO. They are very similar with the difference of perhaps maybe 0.5% on the ratings. Located around the area, and there's a lot of interest on the environmental justice areas as well. So I'm trying to kind of use the data that was available before and whatever I can come up with right now to kind of be a participant on all of this strategies and towards the environmental, justice movement. But like I say, I'm not seeing a lot of interest from the community, so it's kind of hard to push for something when we don't see any pushback. And so, if you know any environmental communities that might be interested or related to the Georgia area that may want to come, kind of participate, we'll be willing to be part of that too.